Right. So, hi, those of you who don't know me, I'm André. I'm the head of physics at the university. I'm a quantum physicist by training, and I thought I'd give a slightly different perspective on. I'm writing eigensystems because in my case it's both the eigenvalues and the eigenvectors which are important. And I wanted to just give the quantum physicist perspective of eigensystems, and obviously that baby over there, that's me, and I'm basically destroying linear algebra and playing with it and doing what I want to do with it. This is I guess how mathematicians view physicists, and between us, I think they're right. Um, anyway, so I'm not going to go into details or anything. I just to give a flavor for how these curious mathematical objects crop up in physics. Now, one thing I like, I think I always put this slide somewhere in all of my talks. So one interesting thing about being a any kind of scientist is that you're kind of building up on other scientists' work, but not necessarily in the same field. So the joke goes that biology is just applied chemistry, chemistry is just applied physics, physics is just applied mathematics, and it's kind of correct. And I guess it's in the spirit that I was invited to present this work here because at the end of the day, yes, I do physics, but physics is just an application of mathematics. Of course, it's an application of a small bit of mathematics, but it's still an application of mathematics. And for those of you who haven't studied physics, well, physics is all about getting to know, or trying to get to know, how the universe works. And of course, we have kind of developed our picture of the universe over the past several centuries. And we could go as far back as someone like Galileo Galilei, who was one of the first people to start realizing that things don't just happen randomly. There is some sort of order in nature. If I throw a mass in a certain set of conditions, then if I had to throw it again under the same conditions, the same thing would happen. And it's this kind of change in perspective, that the universe has some sort of rules and regulations that it abides by, which finally started giving birth to physics, really. So yeah, okay, this is one of the bigger milestones. Then came someone like Newton, who gave us his famous laws of motion and said that you could actually represent nature mathematically. Really, I mean, this is perhaps the biggest contribution to Newton's philosophy, and it's the idea that you can represent position as a vector, hence velocity and acceleration as a vector. You can do the same thing with force. We've heard about what vectors are in the talk just preceding mine. And by using these concepts, you can basically predict how things will change, will move. How a football will move if I kick it in a certain direction at a certain speed. And it was a change of philosophy, and this is why perhaps things took a short while to catch on. But nowadays, I mean, we see all of this as quite intuitive, and in fact, this is how children learn how the world works. This is why they drop things. They're effectively learning about Newton's laws of motion. A few centuries after that, we meet Albert Einstein, who kind of changed a bit how we view the universe, or quite a bit actually. And he introduced this concept of space time, where space time is bent by the masses on it, and everything, including light, basically follows the shortest path in this bizarre bent space time. And again, it's a change of philosophy. The universe space is not just some sort of backdrop, some scenery that we have a play in front of, but we actively participate with space, and space actively changes us. It is a change in philosophy, but it's kind of almost intuitive in a very strict sense. In fact, you can sort of represent it with these sort of rubber mats that you throw martyrs on and so on. Then, at around the same time, we had a completely different change in perspective, and quantum mechanics came onto the picture. And quantum mechanics is still extremely counterintuitive to basically everyone. The quote goes, and I can't remember who it was, maybe the Rock, I can't remember, but the quote goes, if you're not shocked by quantum mechanics, you haven't understood it. And another quote says, nobody understands quantum mechanics. And I still think those two quotes, despite being a few decades old, are still very, very valid. And here we have a complete change in how we model the mathematics underlying the universe. And instead of thinking about objects moving in straight lines and so on and so forth, or geodesics or whatever the case may be, we are thinking about representing objects through some very, very abstract mathematical quantity. It's this psi, this Greek letter psi that I have over there, which represents something. It is just a mathematical object to which we assign some physical meaning to. So there's still kind of this is still being debated exactly what this psi really means. And on the left there's a depiction of one of these wave functions of a hydrogen atom, and it teaches us a lot. We can learn a lot from it. But is it really there, or is it just a mathematical construct that we can use to infer something from? No one actually knows at the moment. Incidentally, the H bar there, for the Maltese people here, I have been trying to figure out whether that letter was first used in quantum mechanics or the Maltese language for quite a while, because they were both formalized in the 20s, and I still don't have an answer. So I don't know whether it's Maltese that inspired quantum mechanics or the other way around. So if anyone has any thoughts on that, please let me know. So let's play on this. Okay, so because this is where quantum mechanics is born, and this is where we start seeing the concepts of eigenvalues and eigenvectors applied to quantum mechanics, applied to physics. Incidentally, this is called the Schrodinger equation, for those of you who have heard the words. Right, so let's get started. Right, so I'm reproducing here the equation before. Now, I'm going to be referring to the Hamiltonian. I don't strictly need to introduce this or define it. It's just something which I will refer to. And this Hamiltonian, this operator, and I'll explain in a few minutes or two what its mathematical, what kind of mathematical object it is. This operator enters into this equation over here, and it gives us basically a differential equation through which we can obtain these solutions psi. Now, this Schrodinger equation has a set of solutions, which I call here static solutions. So they don't, they're a very simple form as regards their variation with time, their variation with t. And it turns out that mathematically, these solutions, which we call eigenstates, are extremely intimately related to the eigenvectors that we've just heard about. And in fact, we can use these solutions to rewrite the Schrodinger equation in a slightly different way. I apologize, I had some kind of things moving, but they're not moving on the screen. So if you see something jerking, I apologize. So we can rewrite this equation, the Schrodinger equation, using these static solutions in the form that you're seeing over here. And here it starts looking a lot like the eigenvalue, eigenvector equation that Adriana just showed us a few minutes ago. And I'll make this a bit more concrete in a couple of slides time. But just to kind of cement the ideas here, we have these functions psi, which, when we're talking about these static wave functions, we call them eigenstates, and they generalize the concept of eigenvectors. So we have seen Adriana talking about vectors, which are, for example, on a two-dimensional plane, 2, 1, or however you choose to write them, 2y plus j, for example. Here we have vectors, but the vector space they operate is a completely different one. It's actually a vector space of functions. Happy to talk about that later on, but I think it's time is of the essence here, so I'm not going to go through the details. And the eigenvalues have a very special physical meaning. So if we look at this equation here, which is the eigenvector, eigenvalue equation for the Hamiltonian H, that has a set of static states, which we call eigenstates, and the eigenvalues, which correspond to those eigenstates, are energy levels. And you can actually measure these energy levels. So if you get an atom, you can actually see what energy levels there are there. So there's a very, very kind of direct comparison or direct link between the physics of the situation and the mathematics that we use to represent it. Just for your benefit, if I take the original Schrodinger equation, that's the thing here on the left, and the simplified, so to speak, equation of for static solutions on the right. I can combine them. I get a very simple differential equation for this wave function psi, and that's how I get the form of psi, which varies over time in what we call a harmonic way. So it's got exponent e to the minus I et divided by h bar multiplied by some psi, which is a function of position, for example. Just to give you some background of how we end up actually, how we, in the end, we actually use these mathematical objects. So let me try and bridge the gap between what I'm talking about here and what Adriana introduced earlier. So first of all, what Adriana wrote about can be kind of succinctly represented by the first line here. So I have a 2x2 matrix, which operator multiplies a two-dimensional vector, and for a special number of vectors, which are properties of the matrix in question, so the eigenvalue, the eigenvectors of that matrix, then the right-hand side is the same vector up to a proportionality constant, which we call the eigenvalue. This is not a general thing. So given a general matrix, this may or may not ever hold. And even if it does hold, it doesn't hold for every vector. There's specific special vectors, as Adriana was telling us. Now I can kind of abstract out all of that and call the matrix M, the vector V, and leave lambda as is. This is the eigenvalue, eigenvector equation that we saw Adriana writing down. Now, in my notation, bold upright letters are matrices, italic letters with an arrow above those are vectors, just to give you a sense for my physicist notation. Now, you can get this equation, and I can get this what I would call the time-independent Schrodinger equation. So the simplified Schrodinger equation on the right there, and you can actually see, there is a 1:1 correspondence between the two. They are identical to each other, up to a few manipulations, so to speak. So on the left we have a matrix M. On the right we have an operator H, and in a very strict sense, these serve the same function. So a matrix M does to a vector V what an operator H does to a wave function psi in its own vector space. Okay, so it's a completely different kind of vector space, but ultimately there's a very close mathematical correspondence between the two. If you want to know more, follow my second year course in quantum mechanics. Same thing for vectors. So the mathematical role of a vector is replaced by this function psi, by this state. And if the state is an eigenfunction of the operator, then we can define an eigenvalue, which here is E. Mathematically, though, these are identical. Vector spaces are a bit different, but mathematically they are exactly identical. So let's go beyond the mathematics now. So this is how we apply the mathematics to describe physical situations. What does it actually mean? I mean, 95% of being a physicist is trying to look at an equation and figure out what it actually means as far as possible. So what does it actually mean? Now let's think about what I would call a simple harmonic oscillator, but a pendulum, for example, or a mass on a spring or something like this. And let's build a quantum mechanical description of this. I'm not going to go into much detail, just to give you a sense for what goes on. To do this, we need to build this fabled Hamiltonian operator, which I just discussed. And an easy trick for situations like this, where we have a pendulum, is that it basically looks like the energy of a classical object. So if I take a quantum mechanical pendulum, its Hamiltonian is basically kinetic energy, green there, p squared over 2m, 1/2 mv squared, and potential energy, 1/2 kx squared. And this gives us the, this is the, if I remove those fancy hats there from the top of on top of the operators, HB and X, that looks a lot like the kinetic energy plus potential energy of a classical simple harmonic oscillator. But now we have an operator H, the Hamiltonian. We have an operator P, the momentum operator. We have an operator X, the position operator. These are not numbers. These are actually mathematical operators which play a special role. Okay, I can't go through the details here, but this kind of introduces a new mathematical richness into our description of nature. So I have this Hamiltonian, and we saw earlier I had the kind of eigenvalue, eigenvector equation based on the Hamiltonian. Here we have an operator, and the eigenvectors are functions. What these functions look like? They actually look like this. So each one of these, from top to bottom, and there's infinitely many more, they are these functions psi, which are the eigenfunctions of the specific Hamiltonian. That's kind of mathematical language. In physical language, if I had a quantum grandfather clock, then if I cool it down to basically absolute zero or near enough, then its state of motion can be represented by, for example, the lowest lying function over there. And if I had to reproduce this, had a billion quantum grandfather clocks, and I checked where they were in position, I would get a histogram, a probability distribution, which looks a lot like the lowest lying curve there, the square of it anyway, but detail. Okay, so there is a physical, very, very direct physical link between the mathematical description and these functions, which are vectors in their own vector space. Okay, so let's try and keep this analogy in mind. And these functions really do describe something about the physics of the situation. We can actually measure these. So here we don't have a quantum grandfather clock. We're actually talking about light, but the description turns out to be identical. And you can see actually these are the same 5 states. So if I go back one slide, here I have 6, but you go 0, 1, 2, 3, 4, 5 from bottom to top. The same 5 states are actually the ones shown here. These are actual measurements in a laboratory. I can tell you how to transform from these graphs to the ones before, but they're actually showing pretty much exactly the same thing, which is fascinating. So it's not just a mathematical description. There is something in there that we can actually measure. And part of what we do is trying to figure out how we can measure this, not on light, which light is light, but building an actual physical grandfather clock, if you want to call it that, and trying to measure these states of motion, these quantum states of motion. That's something we can discuss at length later on. So this is one aspect of how these eigenfunctions and eigenvalues pop up in quantum mechanics. Let me show very, very briefly, and I'm soon finished. Let me show very briefly another aspect of them. And here you might also recognize the eigen part of eigenvalue and eigenvector quite well. So let's say I want to make a measurement. Let's say I want to measure where something is. So I get a ruler and I want to try and measure it. Well, I can find it somewhere, I'd say 1 centimeter, or perhaps, there was an animation there, so I was supposed to see 1, 2, 3, and 4, but for some reason I can't see the animations here. Anyway, or could be at position 4 and so on and so forth. Now, this is how we kind of think about making measurements in the real world. We measure something and we see where it is and jot down the value. It turns out there's a duality, no, not duality, a translation, I would say, between this kind of physical scenario and the eigenvalue, eigenvector relationship. How? Let's take a specific kind of quantum object. I'm not going to talk about the details, but let's say it is, because quantum mechanics is weird, it's like an arrow pointing up and down at the same time. Now, what this means is that the arrow has no direction, and as soon as we make a measurement where we ask whether it's pointing up or down, that's when it assumes a direction, up or down. So we make a measurement, and just give me a second. And no, for some measurements it will point up, for some measurements it will point down. No details. I'm not going to say when it happens and so on and so forth, but sometimes it does this, sometimes it does the other one. And the curious thing is, if I repeat the measurement, let's say I found the arrow pointing up, well, it's going to stay pointing up no matter how many measurements I make. Likewise, if I find it pointing down, it will always be pointing down no matter how many measurements I make. So there's this concept of repeating a measurement and always getting the same outcome, which is a bit like multiplying an eigenvector by a matrix and always getting the same vector, up to a constant anyway. And in fact, it turns out that if I were to represent the mathematical process of measurement, what I have is some sort of measurement apparatus to which I feed this weird state, and I get one or the other out. And actually, it turns out that this measurement apparatus is described by a mathematical operator, which plays the same role as a matrix in Adriana's talk, and out of which I get one of these, one of a number of eigenstates of that operator. So in the same way as Ariana showed us how we can get the eigenstates of these matrices, actually, if we build the matrix which represents, or the operator which represents a measurement, then we can find its eigenstates. And when I make a measurement, I will always get one of these eigenstates. And if I keep making the same measurement over and over, then I will stay in the same eigenstate forever. Okay, so there's just a couple of examples of how eigensystems crop up in physics. I didn't have too much time and actually overstayed my welcome by a couple of minutes. So thank you for your attention. Please do get in touch. I'm going to stay here just in case there's any questions or thoughts or criticisms. Yeah, thank you.
Thank you very much, André. That was very interesting. Does anyone have any questions for Prof. Xuereb?
What is the Wigner function?
Did I have Wigner function? Ah, yes, over here. Okay, so let me, Luke, do you mind if I just share the screen?
Yes, of course.
Very briefly. So let me share. How do I do that? There we go. Okay, so Professor Xuereb there is referring to this Wigner function. So the Wigner function here is what we would call a quasi-probability distribution. So very briefly, if I had a classical object like a football, and it was set up in a specific probabilistic way, I could create 1,000 of these footballs, or 1,000,000, or some large number. I could check what the position and momentum of each of these footballs is, and plot a histogram in 2 dimensions of probability versus position and momentum. Does this make sense, first of all?
Okay.
Now, in quantum mechanics, because of the non-commutativity of the operators, but really because in inverted commas, you can't measure position and momentum at the same time, you cannot build such a probability distribution. But there are mathematically similar objects, which we call quasi-probability distributions. For example, these quasi-probability distributions can actually go negative, which a probability distribution obviously cannot. And a Wigner function is one of these quasi-probability distributions. Now, just to kind of bracket things off, if I were to integrate these distributions along a certain direction, so for example, along the imaginary axis and here, or along the real, so one of them, then I would get a bona fide probability distribution. So for example, a probability distribution over positions or over momentum, and that would always be non-negative. So if you integrate these curves along the imaginary axis, you would get exactly the square of these functions over here. Just to kind of link the two together. But I say there might be another kind of Wigner function in let's say your branch of mathematics, because Wigner was quite a productive fellow. But that's how we use them.
Okay. Another short question. If it's the answer is long, tell me later. Does the time-independent Schrodinger equation have I for complex I in it?
This one over here, yes.
Yes.
So the time-independent, so that's the top right over here. No, it doesn't have an I. It appears in the time-dependent, which is the
time-dependent. Okay.
Yeah.
Does it have an I in it?
Yes, so that's I. That's the complex I here.
Oh, I see.
Okay. And that basically means, in a nutshell, the Hamiltonian H is Hermitian, but that basically means that eigenvalues are always real. And if they are always real, then that I there means that when I take the exponent to the minus I et, I get a harmonic variation, which preserves probability.
Oh, I see. Okay, thanks. Thank you.
You're welcome.
Does anyone have any other questions for Prof. Xuereb?
I think I saw something in the chat, but I'm not sure if, let's see.
It
was fine, man. Yeah, thank you, Anna.
I'd just like to say thank you to André. And also it's very cool for me, right, as someone who is a math and physics student and who is very involved in QM with André, right, to see like 30 people online in a video call talking about Hamiltonians and the Schrodinger equation and these things, and also people from the physics department and the maths department talking about these things. So I think this is a really cool and important thing, and I'd love to see more of this going on.
It was a nice anticipated crossover.
Yes. No, thank you. I mean, I try to create this crossover because I'm a fan of it, and that's how we learn new things about nature. But thanks for setting this up and hosting this, guys.
The only comment I'd add, just as something which, even to talk about my own experience, for me the most shocking maybe appearance of eigenvalues and stuff like this in QM, and maybe, you know, everyone excuse me for being a bit technical here, but I think this will maybe be interesting for people who get it right. When we talk about entanglement, so how correlated things are and stuff like this, the way in which we are able to quantify entanglement is deeply related to what the eigenvalues of the mathematical operators representing this quantum state are saying. And to me, this is very, like I said, shocking almost. You know, how is it that these eigenvalues, by doing this thing, can tell us how correlated systems are? And in some sense, it's very related to graph theory. So the same way in which Prof. Shriha and Luke sometimes have done work talking about eigenvalues in graphs, if you look at quantum states as graphs and stuff like this, entanglement can be described in this way. So I just wanted to add that little thing, because to me it was sort of a very shocking thing.
That just made everything, you know, ever the more enticing in some money. Yes, okay, so now we'll go on to Prof. Muscat's talk, and I think his talk will also shed some light on the stuff which Prof. Xuereb was talking about, like if you think about it as a differential equation, right? But I don't want to preempt and so on. Fidek, Prof.